Alaikum and greetings everyone. I hope you are all doing well. First of all, thank you for joining us today for a webinar organized by IEEE KIET Student Branch 2021. We are extremely overwhelmed to have you all here with us today. I am Sauda Anil, Vice Chairperson at IEEE KIET Student Branch 2021-2022, and I'll be your host for this event. And on behalf of IEEE KIET Student Branch, I humbly welcome you all to this webinar. Dr. Saba Javed is an assistant professor at PAF-KIET and has completed her PhD with publication in IEEE transaction on industrial electronics having an impact factor of 8.23. Her area of expertise lies in applied power and control systems. She has completed her bachelor's from IIEE and proceeded with her master's and PhD at PAF-KIET. She passed both her bachelor's and master's with distinctions, and she has over 10 years of teaching experience in public and private sector universities. Thank you very much, ma'am, for joining us today. Before we begin, all our participants are requested to keep their mics and videos turned off during the entire session. We will have a question and answer session at the end, in which you can raise your hand and the host will give you the opportunity to ask your questions. You can also send any questions or messages to the host through the chat with your name and affiliation at the end. Now, without further ado, we'll hand over the control to our most esteemed speaker, Dr. Saba Javed.
Thank you, Sauda, and thank you everyone for joining this presentation. I hope you all can hear me loud and clear.
Yes, ma'am, we can hear you.
Okay. So, as you all have seen the title in the publicity posters and vouchers that had been shared with you, this presentation is related to maximum PowerPoint tracking of PV system. I have tried my best to make sure that maximum of you, all of you can learn maximum out of this presentation. However, I would really like to mention here that this presentation will be more beneficial for students who are going to pursue their final year projects in the area of power electronics, especially the PV systems. Also, the postdoc students who are trying to join some if you this is from a point of view that recently Sky Electric solar energy company has been launched, and it has recruited many engineers from different private and public sector universities. So a wide opportunity of jobs have been provided by them. So students who are trying to pursue their career, they can also go into them. Also, the engineering students are mostly interested in doing their masters and their PhD abroad. So all those students who are interested in pursuing their masters or PhD in power electronics, they can also benefit out of it a lot. So I have tried to make it as learnable for you as it can. However, if there is something left, so we can further proceed it with some workshop or some other kind of relevant activity that can be held physically. So I'll start this. I have already been introduced to you. So these are the following. Initially, we will start with the title. The title says a simple yet fully adaptive. So we will start our presentation with first explaining what is adaptivity. Here, the term adaptivity basically deals with the literal meanings that say being able to adapt, being able to change your perception, your view, your lifestyle according to your surroundings. So this is called adaptivity. So here, this word adaptive means exactly the same. Another word used here is PSO. PSO here stands for Particle Swarm Optimization. It is an Mppt tracking algorithm, a specialized, customized maximum power point tracking algorithm. So the word maximum power point tracking is here termed as Mppt. Next, you will see PV systems. PV systems are basically photovoltaic systems, and we are all aware of it. Another word used here is PSC, that states partial shading conditions. So all these words that we are being using in the title, I'll be explaining one by one in the presentation so that you will be able to go with the flow. Okay, so this presentation will basically cover the basic introduction, where we will see why do we need a power system, PV power generating system. Why do we need that system? Next, if we have a PV power generating system, then why do we need an Mppt algorithm? What does it mean to extract maximum power from a PV system? We will see the existing work which is found in the literature, the published work that has been so far found very prominent in the area, in this area of research, the gaps that are found in these published work, what are the problems that we have been stated on the basis of the identified gaps. We will then propose to our idea the methodology that how can we overcome all those gaps, provided the fact that eventually we will be having a simplified and fully adaptive algorithm. What will be the advantages of that simplified and fully adaptive algorithm over the conventional way the PSO is used? We will be doing the comparison of the proposed idea with some existing non-prominent work found in literature. We will see the simulation as well as experimental results that will support our claim. Finally, we will see what we can conclude from this whole presentation and what are the future recommendations that can be accommodated to make this to work further on this area. Okay, so these are basic things that we will be covering in this whole presentation. So first things first, starting with why do we need PV systems? As we all can see, the world energy population is increasing significantly. Also, the frequent human movement, the ever-increasing life change in lifestyle, the world energy demand has been subjected to tremendous strain. And this increasing demand of energy has ultimately leads to two major concerns. One is energy sustainability, that we want to refill the energy source all over again. And other is the environmental constraints. Out of these two concerns, the latter has manifested itself in the form of great civil basically it's affecting our civilizations. We can say the environmental constraints are affecting the human beings all over the world. So pertaining to this fact, today the challenge is to tackle the climate change and the global warming by adapting the effective and renewable sources of energy. The renewable sources of energy that include solar energy, rain, tidal wave, wind, turbine, they are all used for electrical power generation over the years. If we compare these renewable sources of energy with the fossil resources of energy such as coal, oil, gases, so they have two major advantages. One is energy sustainability, that is, these sources are coming from the natural resource and therefore we may never run out of it. We can refill them all over again. The next is environmental considerations. If you see, when these renewable sources are used to generate the electricity, they emit very less or no amount of carbon dioxide, and therefore they are very environmental friendly. So collectively, on the basis of these two comparisons alone, that is energy sustainability, they will never run out of these energies, and the environmental friendliness, we can collectively say that renewable sources of energy are an ideal and effective solution to overcome the world energy demand. However, if we see, there are so many renewable sources of energy that I have told you earlier, which include solar energy, wind turbine. Out of all these renewable sources, the photovoltaic energy, which is a solar energy, has gained immense attraction all over the world. This is mainly due to the fact that sun radiates an enormous amount of energy onto the earth's surface on daily basis. And if this energy is harvested properly, we can generate, this is sufficient enough to fulfill the whole world energy demand. This is due to the fact that several countries have commercialized the building integrated PV systems, photovoltaic systems, and have also offered subsidized feed-in tariff commercial activities to increase the adoption of solar form of energy. This is not the only fact that is why we prefer solar energy, but also out of all the available renewable sources, solar or PV photovoltaic systems have some inherited advantages. These advantages include low maintenance. They have low cost. They have low maintenance, and they are very much environment friendly as compared to other sources of energy. However, despite of all these tangible benefits of the PV systems, the main hindrance in the public acceptance of solar systems or the PV systems is the initial capital investment, which is very high. This high investment is mainly due to the high prices per module. Although over the past few decades, the prices per module have been decreased significantly, but still the PV energy or PV systems are way above than conventional electricity. They cost way above than conventional electricity. Therefore, it is since they are expensive in comparison to the integrated energy that we are getting from the conventional sources, it is therefore imperative that whatever energy is produced by a PV system or a module should be optimally extracted. Several research and work has been done in the area of photovoltaic system in both directions. One way is to improve the cell technology so that the prices per module will decrease significantly. And the other area of research which has gained immense attraction of the researcher is to make algorithms that would be able to extract maximum power from a PV module or a PV system. Okay, so basically the idea is the Mppt algorithm, which is a maximum power point tracking algorithm. The maximum power point algorithms are basically designed in a way that they can extract maximum energy from a solar PV system under any environmental condition. Now the point comes, what does I mean by any environmental condition? The ideal condition states that a solar panel or a PV system should be mounted in an area when there is no shading. By no shading, I mean that the solar panel should be receiving the full illumination or full shading from the sun, full irradiance from the sun. However, practically due to unforeseen constraints, this is just not possible because mainly the PV systems when integrated in dense urban areas are subjected to high buildings. So shading is unavoidable. The shading could be due to the neighboring building, a tree shadow of a tree or some poles, but there are chances that whichever panel or the module or PV system you have mounted will be subjected to some shading due to some building, boards, poles, or the trees. However, if we see when the solar panel, when the PV system is subjected to the shading conditions, it started to behave differently. So basically, on the basis of the shading and unshading condition, two forms of PV systems can be constructed. If you see this figure 1, it has two strings of PV module A and B. Each string has 3 modules connected in series, module 1, module 2, and module 3. And if you see, each module has a bypass diode connected in parallel. Why do we need to connect a bypass diode in parallel with a PV module? A PV system is basically comprises of series parallel combination of several PV modules. So in this example, I am explaining a PV string having 3 PV modules connected in series configuration, and each module has a bypass diode connected across it. Okay, the difference between the string A and the string B is in module 3. The modules in string A, all the modules have same insulation. None of them is shaded, none of them is gray, none of them is dark. So they are all receiving equal amount of radiation from the sun. However, in case of this string B, you see this module, this shaded module PV3 is basically shaded. It has a dark shade. This is to represent that it is not receiving the sun radiation. This module is shaded by either tree, clouds, or poles, or some neighboring building, but it is shaded. Okay. So why do we need these bypass diode to connect across each in parallel with each PV module? This is to make sure that when any of the PV module in a PV system is shaded, it keeps on behaving as a generator. Usually, a phenomenon known as hot spot occurs when any of the PV module is subjected to the shading condition. This phenomena basically explains that the module which is shaded will start to behave as a load instead of a generator. So what will happen if such kind of situation is came across? You see, here we have few curves, curve 1, curve 2, and then a green curve shown here. This is basically a voltage versus current curve. Along the x-axis we have PV voltage, VPV, and along the y-axis we have voltage PV current, which is IPV. And we have another graph plotted here, which is basically a PV curve, a power voltage curve. So along the x-axis, we have the voltage, and along the y-axis, we have the power. So the objective is to extract maximum power from this PV system, okay? So if you see, in case of the string A, where all the modules are receiving same insulation and none of the module is subjected to shading, the curve 1 is obtained, and the beauty of this curve is that it has a unique peak. You see, this is a unique peak. This is the point where maximum voltage and maximum current will be obtained. I hope you all can see the cursor here. So this is where you will obtain the maximum power. But in the string B, when a module is subjected to shading condition, instead of a unique peak, now the curve 2 is subjected to two peaks. One is here, this is the red peak and a blue peak. So when there is partial shading condition, what happens due to the blockage diode, due to the bypass diode that are connected in parallel with the module to make sure that the module keep on behaving as a generator, the PV curve is subjected to multiple peaks. In this case, it is 2 because we have two different type of shading. Module 1 and Module 2 are receiving same insulation, whereas Module 3 is subjected to some shading condition. Now you assume we have a large PV array with more than 10 or 20 PV modules connected in series parallel combination. And out of 20, 3 modules are subjected to partial shading condition, but each of these 3 modules are having different type of shading. One is more shaded, other is lightly shaded, and the next one is mildly shaded. In such case, you will be having 4 different peaks in a IV curve because you will be having 4 different shading patterns. Few modules are not shaded, some is mildly shaded, some is lightly shaded, and other is fully shaded. So it means as much as shading pattern you will be having, as much as peak the curve will be having. This problem, when there are multiple peaks, then it is very difficult to differentiate between a local and a global peak. If you look at this curve 2, which is a voltage versus power curve, you will see the curve 2 has 2 peaks, the red and the blue peak. And the maximum power from the naked eye can be seen at this peak, which is blue in color. However, in case of multiple peaks where there are more than 2 to 4 peaks, it is very difficult for an algorithm to differentiate between a local and a global peak. So now I'm using the term local peak and global peak. When a PV array is subjected to shading condition, it has multiple peaks. So we call these peaks as local peak. And out of these all local peaks, the peak with maximum power is termed as global peak. And the objective of a maximum power point tracking algorithm is to track that global peak. An efficient maximum power point tracking algorithm is supposed to be capable of differentiating between a local and global peak and converging the particles or the optimal voltage at the global peak. So it means if we look at these two conditions, and if we want to avoid these multiple peaks, what we can do, we can eliminate these bypass diodes from the algorithm. And what we will get is we will get a curve which you can see here in the green color. This curve now has unique peak. It has only one peak. Although the module is still shaded, but we have removed the bypass diode, and therefore the curve now has a unique only single peak. However, the problem here is that out of these two peaks, the curve with the unique peak, when the bypass diodes are removed, has less power. If you see, when the bypass diode are connected, power is near 40, and when the bypass diode is disconnected, it is near 30. So it means that it is recommended that one should connect bypass diode in parallel with each module to improve the overall efficiency of a PV system. If these bypass diodes are not connected under shading conditions, the PV panel, the maximum power across the PV panel will be reduced, so the overall efficiency of a PV system will also be reduced. Another important thing to be noticed here is the blocking diode, which is connected at the end of each string. These blocking diodes are connected to make sure, since several modules are connected in series parallel combination, and we know in series voltages are same. Sorry, in series current is same, whereas in parallel voltages are same. So in case any of the module is subjected to shading and the parallel strings are having mismatched voltages, so these blocking diodes will prevent the reverse current to flow from the module. So basically the blocking diodes are connected to make sure that under shading condition and mismatched voltage condition, no reverse current flow through the circuit. On the basis of these two shading conditions, if you see, this is what happens when the shading, when there is a cloudy weather and the weather is changing very rapidly. So you see operating point here. Operating point means the maximum power point. As the insulation will keep on increasing, you see here the rapidly changing irradiance with time के साथ जो sun radiation है, it's keep on changing, and with the change in radiation in sun, you see the maximum power point is also keep on changing. So it means that under rapid fluctuation, Mppt maximum power point will keep on fluctuating or changing. So it is really a very challenging task to extract maximum power from any PV system when it is subjected to shading conditions. So now that we have discussed two types of installation of a PV system, one when it is installed in an area where each module is receiving uniform insulation, and one the area where the module, any of the module or few of the module is subjected to the partial shading condition. And when few of the modules are subjected to the partial shading condition, multiple peaks in PV curve are obtained. And when multiple peaks are obtained, then an algorithm is supposed to differentiate between a local and a global peak. And here the global peak is referred to the peak that has maximum power. Okay, so two categories of algorithms are also found in literature. One is to deal with uniform insulation and other is to deal with partial shading conditions. If we talk about the uniform insulations, these approaches or MPPT algorithms are known as conventional MPPT algorithm, and few most widely used and prominently known algorithms include perturb and observe. Most of you may have heard of it as PNO. Hill climbing, HC, and incremental conductance. These algorithms work absolutely fine when the PV system is subjected to uniform insulation. However, they are not capable of differentiating between a local and a global peak when a PV system is subjected to shading condition. Therefore, these algorithms are not suitable to apply under partial shading conditions. Okay. The reason why these algorithms are not capable of differentiating between a local and a global peak, because these algorithms basically work on the principle of power change. Okay, if the power change in one iteration is greater than the power change in the previous iteration, then the particles will keep on perturbing in their continuous direction, which means they only have the information of the change in power. So even if a particle has reached to a local peak, all the other particles will converge to that local peak without exploring the global peak. So once any of the peak is explored, the particle will keep on combining or converging to that peak. It means that there is a chance that accidentally any of the particle converge to or reach to the global peak. In that case, these algorithms will successfully track the GP. But in most of the cases, if the particles are randomly initialized, there is a chance that the potential peak, the optimal peak, or the global peak will be skipped. Following this fact, when a PV system is subjected to partial shading conditions, an alternate approach is used, which is employing the evolutionary algorithm-based MPPT. Several evolutionary algorithm-based MPPT are found in literature, and the reason why we prefer evolutionary algorithm-based MPPTs, because evolutionary algorithm is a search-based optimization algorithm and is capable to deal with non-linear multi-model functions. Although MPPT tracking has only one output, which is power, But due to the non-linearity of the curve and the multiple peak involved under the partial chaining condition, many researchers are calling it as a non-linear stochastic problem. So, evolutionary algorithm has inherited advantage because they are search-based optimizations. So ideally they are capable of searching the global peak and then converging the particle to that global peak. Several evolutionary algorithms are found in literature. You can see a list of those algorithms who have been prominently used. Albeit all of these algorithms, there are many other that you can found in the literature, but these are one who have been prominently used in their modified version, in their standard version, and so on. But out of all algorithm, which is this last one, has been very widely used following its inherited advantages. It has three major advantages. It has fast computation, it has easy implementation, and it has lesser number of parameters to be tuned. Due to these three major advantages, researchers preferred particle swarm optimization algorithm for MPP tracking of PV systems. So in this presentation, now we are proceeding for the maximum power point tracking of a photovoltaic system when it is subjected to partial shading condition, when the PV curve has multiple peaks. And with this multiple peaks, we will be using an evolution PowerPoint tracking of a PV system. So I would first like to explain what is particle swarm optimization. As the word says, particle swarm optimization. In particle swarm optimization, we initialize some particles randomly. And the number of particles that we initialize is known as population size. You can initialize with 3 particles, 5 particles, or 100 array size. If you have a big array size, you can initialize with large population. If you have a small array size, you can initialize with fewer number of particles or small population size. So each particle that you are initializing contain a distinct position and perturbed on the basis of a velocity factor that is given by Pso. Here you see this equation. This is basically phi is the velocity factor that each particle calculate, and on the basis of this phi, it perturbed or move its position from its original position. So if you see this velocity equation, which is a very important equation for conventional, this is basically conventional particle swarm optimization that was first introduced by Kennedy. So if you see, it has three factors: initial velocity phi, P best, and G best. This R1 and R2 are the random numbers. It means they are initialized randomly and will change in each iterations. So R1 and R2 can vary can be any number between 0 to 1. This C1 and C2 are the gains. You can tune these gains on trial and error basis, or you can make them increase or decrease linearly. So in most of the published paper, these gains are either chosen arbitrarily or are designed in a way that they keep on increasing and decreasing linearly. Two important factors are this P best and G best. If you see, P best means local best information. It means the local best particle has its own position. Xi is the current position of the particle, and P best is the best position in power. Particle's neighbor's position is known as the local best position. A particle with its neighboring positions is known as local best. So this is termed as P best. So what each particle calculate its velocity on the basis of difference of its own position with its neighboring best and the global best, and this velocity factor is added into its current position, and the new position is calculated. Okay, so if I sum this up, what happens? Initially, we initialize the particles randomly. Each particle attain a position. Out of each particle, one particle will be having the maximum global best position, and then each neighboring particle has local best position. So what we do, each particle calculate a velocity factor following this equation. That velocity factor is added into the particle's current position, and on the basis of sum of these two factors, the new position of the particle is calculated. To represent position displacement, I have used X here. So you can see this is the displacement from its initial position. Okay. Although conventional PSO were effective enough to track the MPPT algorithm, but still two modifications of conventional PSO are found in literature. One is by introducing an inertial weight factor, and other is by introducing a constriction factor. If you look at these two factors, you will see the only difference between the two is that inertial weight is multiplied with the velocity factor only, and the constriction weight factor is multiplied with the whole equation. But this is not the only difference. The inertial weight, this factor W, can be either fixed or dynamically varying in the range from 0 to 1. Again, you can make it linearly increasing or linearly decreasing, or you can choose any fixed value from the literature. However, this constriction factor K depends on the C1 and C2. And if we go back and see what C1 and C2 are, C1 and C2 were the constants of the local best and the global best position. So one, let's say local best को मैं cognitive factor कह रही हूँ और global best को मैं social factor कह रही हूँ. So C1 and C2 are the cognitive and the social factor. So this constriction factor K basically depends on these cognitive and social factors, and therefore with any change in K, these two values will also be changing, or vice versa. So basically, these two factors were introduced to ensure that the algorithm track converges to the maximum peak very fast, and also to ensure that algorithm precisely locate the GP. So these were the two objectives on the basis of which the overall performance of any MPPT algorithm is judged. The computational capacity, which means it should be fast computation wise, and it should be accurate enough to differentiate between a local and a global peak, irrelevant of how many global or local peaks are there. What is the difference between a local and global peak? Algorithm should be precise enough to differentiate between the two. Okay. So on the basis of these cognitive and social factor, constriction, and the inertial weight, in the literature, you will see 6 variants of PSO has been found. These variants and the equations have been presented here. And the only difference in this, the first 3 equations has inertial weight, the last 3 equations has constriction factor. And the difference in these 3 equations is, one is the full model with having both the local and global information. The other two have either the global information or the local information. So one is the full model, the one having global information is the social model, and the one having the local information is the local model or the cognitive model. So we can say that on the basis of full model, social model, and cognitive factor, we can have 2 groups of 3 variants. First 3 variants are with inertial weight, and the next 3 variants are with constriction factor. Okay. So now it is very important to mention here that the PSO parameters mean the constriction factor C1, the cognitive factor C2, the inertial weight W, the constriction factor K, and the population size NP. Here NP represents the number of populations, number of particles that you have given initially. All these parameters play a very significant role in the overall performance of an algorithm. When I say overall performance, it means the computation capacity, the speed with which the particles converge to the GP, and the overall accuracy of the algorithm to track any kind of PV with any number of local peaks. What we found in literature, several work related to PSO are found in the literature, and here I have listed few most prominent ones. These references are mentioned at the end. If there are few observations that we need to make from the literature review, at first you will see variant. Here the word variant says the type of model that they have used. F is for full model, SO is for social only model, and okay, because there are only 2 models. C would be used for cognitive model, but But to my surprise, but to everyone's surprise, the work found in literature has either used full model or a very few work have used social only model. None of the work found in literature have employed the cognitive only model for the MPP tracking of the system. So the first thing to be noted is, despite of the fact that the social only model you see here has lesser number of parameters to tune, it do not have C1R1, it do not have the information of p-base, so it is a more simplified variant. So why in the literature this simplified variant is used lesser than the full model, which has more number of parameters to be tuned and more calculations to be involved. So this is our first observation. Next, what you can see from here, mostly the control variable used is duty cycle. It means the converter that has been designed or the controller that has been made is usually a duty cycle based control. A very few work based on the voltage based control have been found in the literature. Number three, if you look at the parameter, you will see the parameters are arbitrarily selected. The value of C1 and C2 are randomly chosen in most of the cases. The population size is either very low but fixed or either very high. You see it is either 3 or 50. Okay, so inertial weight in most of the cases is in between 0.4 and 0.5. Again, it is arbitrarily selected. By adaptive, when we say adaptive algorithm, it means that every parameter should change with the change in the curve behavior, with the change in particles position, with the change in number of iteration. But what we can see from the literature, in most of the cases, the proposed algorithm or the conventional or the modified version of the PSO algorithm used have fixed value of each parameter. So whatever the constraints are, whichever iteration you are running it, whatever is the type of curve and the size of array, these parameters will remain fixed, which obviously in turn will affect the overall performance of the algorithm, except for the work find in 21, which has adaptive parameter. If you see this, the C2 is fixed, but C1 depends on C2 and some value. So every time with the change in this AI, the parameter will keep on changing. And AI depends on what? It depends on the global best power, the current power, and the peak-to-peak voltage. So it means if the array voltage changes, if the global best power changes, or if the current power changes, with that the C1 will also change. So such kind of algorithm is called adaptive algorithm, in which the parameters adapt themselves according to the change in their surroundings. But most of the work found in literature disappoints us in the way that they do not fulfill the requirement. Okay, so now we will see what is a conventional PSO. Now that we know, we will see how does it work. To explain you the working of a conventional PSO, I have chosen a work from the literature, a very prominent and well-known work found in the literature with many number of citations, and the parameters are taken from that work. So you see C1, C2, which is cognitive factor, social factor, inertial weight, and population size. All these parameters are chosen from that work. The PV array used has following specification. The short circuit current is 3.8 ampere. The peak to peak voltage is 70.1 and peak current is 3.5 ampere. Maximum power of each module is 60 watt and the open circuit voltage of each module is 21.1 volt. Now, if you see this curve, it's a PV curve. So it has voltage along the x-axis and power along the y-axis. The voltage varies from 0 to 200, whereas I told you that open circuit voltage is 21.1. What does that mean? It means that this PV system has 10 modules connected in series. So when 10 modules are connected in series, their voltages will be added and we will have maximum voltage of 210 volts. So this PV system has 10 series connected PV modules with it. Okay, when it has 10 series connected PV module, it has 1, 2, 3, 4, 5 peaks. It means out of 10 modules, 5 modules are having non-uniform insulations, different type of shadings. Each module is subjected to different type of shading. So this curve have multiple peaks. Out of these multiple local peaks, each peak is represented with LP. The power across each peak is represented and the voltage across each peak is represented. This peak has maximum power. And if you see, the difference between this global peak and the local peak 3 is only of 17 watt. They both have a difference of 17 watt only. Okay, rest of other two peaks, local peaks, have a very less power difference. So now we want conventional PSO to track this GP. At this global peak, the voltage is 146 volts. So it means if the particle has converged to 146 volt, it means that maximum power point has been tracked. Okay, so this is our objective. Now I'm moving to the working of conventional PSO. As I said, the population size was 5. So initially we will throw 5 particles. Now there is an idea. We are randomly initializing the particles. What I can see from this curve is that the potential peaks, the 4 potential peaks are lying in the range from 60 to 200 volts. You see, the potential peaks are lying in this range. So if I see this, I have initialized the particle in the similar manner. Along the x-axis is the array voltage, and along the y-axis is the number of iteration. So we will be seeing here iteration, how does the algorithm behaves iteration wise. Okay, so in the first iterations, 5 particles are randomly initialized in a way that each particle is equidistant from each other, and the particles are distributed from 60 volts to 200 volts because the potential peaks lie within this range. The potential peaks lies within the range. So इस range में algorithm has to search for the global peak. Okay, so this dotted line shows the voltage at global peak 146 volts. So when the particles will converge to this line, it means that the maximum power point has been tracked. Okay, so you see we have 5 particles and V3 is encircled. This encircled particle means right now this particle has the best position, which means it has the maximum particle. So what should happen? In the next iteration, on the basis of velocity factor, each particle have to perturb in a way that each particle will try to attain the best position. Each particle will try to come to this position. So if I move further, you see in the second iteration, each particle has perturbed from its previous position. You see that? However, there is a problem. What's the problem? This particle with the best position has no change in its position, still it is perturbing. If the particle has no change in its current and the previous position, then what's the point of perturbing it? It is adding an unnecessary computation burden to the algorithm. However, conventional PSO work this way. It keeps on perturbing each and every particle whether it is contributing significantly or not. So this is the problem number 1. When there is no change in previous and current position, there is no need to perturb. However, each particle has been perturbed, and again this particle V3 has attained the best position. As I move to third iteration, you see now this particle V2 has come to the best position with a voltage of 139 volt. So now it is at 146 is the global peak voltage, and this particle has attained 139 volt. And you see again there is no change in V3. V3 has no change in the particle's position. First thing. Next, you see that V4 while perturbing has come very close to the V3 and is exploring an already explored region. This region, this closed region has already been explored by V3. So there is no need for V4 to come and jump into the same region. So we have two problems. One is the particle which has no change in its current and previous position should not perturb. The region that has already been explored should not be explored by other particles. There is no use of exploring an already explored region. Okay, so these are the two problems. So as I move further to the fourth iteration, you see V5, this fifth particle has also jumped into the region of V4. V1, the first particle has also jumped into the region of V2. And now third problem has arisen. Particles are overlapping. While we are searching a peak, what is the point of overlapping the particle? Either the GP is tracked or it is not tracked. Even if a single particle has attained the GP, it means naturally all the particles will also converge to that peak. So there is no point that the particles keep on overlapping one over each other. Say, so as I move further, now you see the GP has been tracked. This line has been successfully tracked, and still particles are keep on perturbing. You see GP is tracked by this particle, which is V4. It is at 146.1 volt, and the difference of other particle from it is not. These three particles are not having not more than 5 volt difference between them. But as I move further, you will see it will still keep on perturbing. The particles will still keep on perturbing. Now the conventional PSO work in a way, even though the GP is tracked by a single particle, the algorithm will keep on working unless all the particles has converged to the GP. So this basically adds an unnecessary computation burden to the PSO. If the GP is tracked by a single particle, it means that all the other particles will now eventually, if the GP has been explode. And when the GP is explode, then all the other particles will also be going towards the best particle. So there is no need to keep on executing the algorithm and overburdenizing the computation load by perturbing the particles again and again. So now we come up with the four basic gaps that are found in literature. Number one, the parameters are selected arbitrarily, they are not adaptive. A particle should know that there is no change in its current and previous position, and therefore it should not be perturbed. Okay, number one, the population size of the algorithm in each iteration should be reduced. For instance, if initially 5 particles are perturbed, the particle with no change in its position should not perturb, and in the next iteration there should be 4 particles only. Okay, likewise the algorithm, likewise, since this algorithm has random numbers, and when an algorithm has random number, it is very important to run algorithm numerous times to say something conclusively about the algorithm. What we can see in the work found in literature, that algorithm is only run once, and the results are extracted on the basis of that single run. However, when there are random number, there is a chance that if a particle is successful in one run, it may not be in the other run, because random number means the numbers will be changing in different patterns, in different fashions. So it is very important, when any algorithm, any theory, any idea has randomness involved in it, it should be executed multiple times to see the overall performance, or overall to see or judge the overall performance of that algorithm. So there are a few things that we have to see. We want an algorithm which is adaptive in nature, that knows the area of region which has been explored and do not jump into that region, that knows the initial and current position, initial and previous position of the particle, and do not perturb that particle, which is not adding any significant information to the exploration process. An algorithm that keep on avoiding the unnecessary overlapping of the particle. The algorithm that should know that GP is explored by a particle and further more execution is not required. So we need a smart, intelligent, basically an adaptive algorithm. So next we are moving to that algorithm, but before moving to that algorithm, we will see, as I told you, that random number means an algorithm needs to be run multiple times. So we are going to propose an algorithm which is adaptive and will be capable of addressing all the problems that I have mentioned to you before. But as we have said, we will judge that algorithm by running it for 100 to 200 times, and will collectively see by analyzing the 100 and 200 runs data, that for how many runs the algorithm was successful and how many times the algorithm trapped to any of the local peak. Okay, so basically we will be using a tool known as run length distribution tool. This are known as RLD analysis, run length distribution analysis. The beauty of this analysis is, although this analysis has never been used for MPPT algorithm, and it is first time proposed to, but have been used in different applications. So we are using it for the first time for the MPPT algorithm. The reason why it was not used, because I told you in most of the published paper, only single one results have been displayed, which is not satisfactory to say anything about the performance of the algorithm. So it is proposed that algorithm should be analyzed by means of some tool. So what would this RLD analysis do? This run length will give you a graph, and this graph will tell you the probability to success of your algorithm. Okay, it will tell you if you have run the algorithm 100 times. So for out of 100, for how many runs your algorithm was successful, and in how many runs your algorithm failed to track the GP. So if your success probability is 1, it means algorithm was 100% successful in all the 100 runs or the 200 runs. But if the success probability is 50%, it means out of 100, the algorithm fails to track the GP in half of the run. So the one information that this RLD plot will be giving of the success probability of your algorithm. The other information that you can extract from this RLD plot is how many runs converge to how many evaluation. For example, as I was explaining you the conventional PSO, we see here that this conventional algorithm took 6 iteration to converge to GP. And I have shown you the 6 iterations only. If I keep on running this, so it will keeps on running until this fifth particle has also explored the GP. So it means it can exceed up to 8 iterations. So if you see 8 iterations and we have 5 particles, so 8 multiplied by 5 means the overall count will be 40. 40 perturbations were there. Do you understand? The algorithm is taking 8 iterations and the number of particles initialized are 5. So the number of perturbations are basically 40. 8 5s are 40. Right? So to judge the overall performance of an algorithm, we need two things: the success probability in how many runs the algorithm was successful, and the number of evaluations, perturbations that the algorithm is taking. The number of evaluation tells us about the speed of the algorithm, the computational capacity of an algorithm, and the success probability tells us about the accuracy of the algorithm. And I told you these are the two parameters on the basis of which we judge a maximum power point tracking algorithm. So now we have defined the problem statement. We need a fully adaptive algorithm. We need a simpler structure, lesser number of parameters, but the parameters should be adaptive. Algorithm should be able to precisely locate the GP. Algorithm should be run numerous times to see the overall performance of the algorithm. Okay, so these are the problems that we are going to address with the help of the proposed adaptive algorithm. The same PSO algorithm I am using, we have just modified it a little bit by making its parameter adaptive. First thing, I have ignored the local best information. So basically, I am using the social only model. Okay, why I am using social only model? Because it has lesser number of parameters to be tuned. I have restricted random numbers as well. Previously, the conventional PSO was varying random number from 0 to 1. I have restricted them between 0.1 to 1. So the random numbers will now only vary from 0.1 to no value lesser than 0.1, no value greater than 1. Okay. Instead of cognitive constant, social constant, constriction factor, inertial weight, I have used only one factor, which is k. And this I shows that this k is adaptive for each ith iteration. In each ith iteration, the value of k or ith particle, the value of k will be adaptive. And this k will be, the value of this k will depend upon the difference of the global best position and the particle's own position. Also, the control we have used is a voltage based control. So instead of x, now you can see I am using v. If I will be using the duty cycle based control, here I would use t. So this is basically a voltage based control. So this k will change its value depending on the difference of these two particles with this factor Vmax. What is Vmax? Okay. A very important thing that has introduced to make adaptive, the algorithm should be adaptive to the size of array. If the size of array is large, it should choose the maximum allowable perturbation to a certain value. If the size is small, it should allow small perturbation of the particle. Perturbation, by perturbation I mean change in position. If particle has large change from its previous and current position, there is a chance that the peak may get skipped. If particle has have long jumpings, it means it can skip the potential peak. So it is very important to define this factor. If you have a large array size, you can keep this value large. If you have a small array size, you can keep this value small. So you see, I am choosing this factor Vm and Vx on the basis of population size, upper and lower bound, the open circuit voltage, and the number of bypass diode connected. ND is the number of bypass diode. VOC is the open circuit voltage, NP is the population size, HA and LA is the bound where the potential peak lies. For this example, it was between 60 and 200. So this is that bond. Okay? So this is the constraints that we have added into the proposed methodology. Now you see, again, the PV parameters are same, the population size is same 5, that bypass diode connected is 1, Vmax is restricted to 10.5. We have allowed a maximum perturbation of 10.5 only, and this VM is calculated using this formula, using the open circuit voltage and number of bypass diode connected. Right? So the open circuit voltage is 210 volts. Since we have 10 series connected module, the number of bypass diodes are 10. Each block will be having 10 diodes. I'm just winding it up. Okay. So if we see this proposed algorithm, you see initially particles are initialized in the similar fashion. In the same V3 particle has best position. In the next iteration, the particle which was having the best position in the previous is now not being perturbed. In the next iteration, it is not perturbed. So instead of 5 particles, in the next iterations, only 4 particles are perturbed. So NP is decreased from 5 to 4. So we have made NP adaptive. Also, you see, now this second particle has successfully tracked the GP in the second iteration. So if you see, by the third iteration, since it has already tracked the GP and it is the best position, so it has not been perturbed, each particle is restricted to their region of exploration. If I move to the fourth iteration, you see no particle is jumping into the region of exploration of other particle. It is restricted here, this one is restricted here, this one is restricted here. So when we go to the fourth iteration, you will see in the fourth iteration, this particle has also attained the GP. And by the fourth iteration, the population size is reduced to 1 only. So it means the algorithm is now taking over all the 3 possible solutions. Number 1, that population size NP is made adaptive. How NP is made adaptive? By not allowing the particle which has no change in position to perturb. So in the second iteration, this particle is not perturbing. In the third iteration, this particle is not perturbing. And in the fourth iteration, none of the particle is perturbing instead of this. Why none of the particle is not perturbing? This is due to the reason that we have not allowed the particles to interfere into the region of exploration of other particles, because we don't want particle to explore in already explored region. So by adaptive mechanism, we would be capable to make sure that our algorithm behaves intelligently and tracks the GP in maximum number of iterations. So here your GP is tracked in 4 iterations. And if you see, the perturbation count for conventional PSO was 40, and here it will be equals to what? Initially we have 5 particles, then we have 4 particles, then again we have 4 particles, and then we have 1. So it means it is equals to 14 perturbations only. In 14 perturbations, the algorithm has successfully tracked the GP in comparison to the conventional PSO, which was taking 40 perturbations. To further show the efficacy of proposed algorithm, we have increased the population size to 7. 7 particles are sent initially, and with the large population size, still the algorithm successfully tracked the GP in 2 iterations. In first iteration, population size is 7, while in second iteration is 6 only. This best particle is not perturbed in the next iterations. So it means the algorithm successfully tracks the GP in 13 iterations. So it means an adaptive algorithm with a simplified structure is capable to address both the problem, the overall performance of the algorithm and the overall behavior of the algorithm. Here we have a block diagram of the algorithm. Since we are running shortage of time, I'm not going to explain this block diagram, while it is very self-explanatory. So if you have a look at it, you can be easily able to understand what does this algorithm, how does this algorithm is proceeding. So I'm directly coming to the simulation and the experimental setup. Okay. So we have the same parameters of the PV panel. We have used a chip converter because it has both the up work and boost capability. So we have used a chip converter as an Mppt converter. The PV array parameters are exactly same. We have used a fuzzy logic controller for the control. Okay. And we will be comparing the results of our proposed algorithm to the 2 very well-known work found in the literature. So I am jumping to the results directly. And if I show you, you see this is the PV curve of the algorithm, the proposed algorithm, and the two most prominent work found in literature. And you can see that difference clearly. The proposed algorithm, each particle has a distinct position and the GP is successfully tracked in lesser number of perturbation as compared to the other two algorithms where there is too much overlapping of the particle, jumping of particle from one region to another region, unnecessary computation of particle. So this particle is not only efficient in terms of tracking accuracy, but it is also in terms of tracking speed. We have also tested the proposed algorithm for a full day profile from 8 a.m. to 6 p.m. from morning to evening. It's nearly 8 hours, I think. And if you see the algorithm, 10 hours for 10 hours, okay. And if you see the algorithm successfully tracks the both the reference and the major powers are overlapped. So the algorithm successfully track the GP. These deeps are shown. These dips are representing the shading conditions. So during this time span, 4 shading conditions were come. However, the algorithm were able to successfully track these shading conditions as well. And now this is the RLD curve. Now you see the proposed algorithm is shown with green. And for each this data is for 3 different curve 1, curve 2, and curve 3. And you will see for each curve, the algorithm has successfully tracked the GP. Success probability is 100% in 13 evaluations. This proposed algorithm successfully tracked it. The algorithm was run 100 times. So it successfully tracked the GP in all the 100 runs, whereas the other two algorithm either has 96% probability, 95% probability, and in case of some curve, the probability is even less, that is 43%. Here SR is the success rate. So here the success rate is 43%. 43% means that the algorithm failed to track the GP in 37 runs out of 100. The algorithm got trapped to the local peak in 37 runs. So it means in terms of tracking accuracy and in terms of speed, the proposed algorithm is way better than other algorithm. Now we will come to the experimental setup. You see, this has 4 different curves, 4 peaks, 1, 2, 3, and 4. This is an experimental curve from the oscilloscope. Okay, why this is so? Because we have 4 modules. One is unshaded, and other 3 modules are covered with different shading sheets. Because it is impossible to generate natural shading, so we have created artificial shading of different grades to make sure that we have a multiple peak curve. So you here see we have experimental curve. This is the experimental setup. Here I would really like to say that experimental results are in accordance with the theoretical results that you can see from this presentation. However, if any of you is interested to see how can we construct a Simulink model or an experimental setup of a PV model, how can we generate these results, how can we code this on MATLAB or make a Simulink model, we can arrange a workshop for it, hands-on workshop, physical workshop where you can interactively see how can you use MATLAB to design a PV simulator, or how can a PV simulator be used in MATLAB, how can these MPPT based simulation being done. If you are interested in seeing all this, so we can further have an extension of the seminar as a workshop where we can have a 7-day workshop so that you can have, or 3-day workshop, depends how much time you have or how your interest is. So at least we can learn how to code a maximum PowerPoint tracking algorithm, how to design it on MATLAB, how to simulate it, and then how can we construct it experimentally and get the desired result. If I show you, all these results are taken on oscilloscope by using the experimental setup, by using 4 PV modules. So you see these results are from the experimental data. So this is all with my presentation. With this, I'll wind it up. It was a little detailed. I know how much you have done from this presentation, but I hope it was beneficial for most of you. If you have any questions, anything, you can ask me, please.
Thank you very much. It was a very informative session, and I'm sure that everyone else in this meeting feels the same way. If any one of the participants has any questions, kindly raise your hand so we can unmute you, or type the question in the chat box along with your name and affiliation. Ma'am, earlier during the presentation, we did have a question. This question is, can we use Gurobi algorithm for MPPT, as the Gurobi algorithm is the world's fastest solver and also guarantee the global optimal point?
Sorry, repeat the question. I could not hear it. I was going through the chat window.
Right, ma'am. We got the question. Can we use Gurobi algorithm for MPPT, as the Gurobi algorithm is the world's fastest solver and also guarantee the global optimal point?
Okay, now it depends. See, we have multiple algorithms search algorithm that we can use. Important to see that what is the computation PV array, then maybe we can go for that algorithm. But if the PV array is small and shading conditions are strong, then we have to see whether that algorithm would be feasible for our PV system or not. So it's really depends on the constraints and the considerations where you are using a PV system and what kind of extraction do you want from that system. So we cannot say, and we cannot give any final verdict about it that this algorithm is good or that is not. There are several research papers who claim that there are algorithms better than particle swarm optimization. So there is no final verdict on that. It depends on the kind of PV system, the array size that we are using, the situations, environmental conditions where we are installing it. So it depends. Any other question?
Yes, ma'am. Some participants are requesting if the presentation can be sent to them, since it's very fruitful and contains a lot of information that may help them.
I don't know if it is in your protocol, you can share with them. That's your decision.
All right, ma'am. Thank you very much. Does anyone have any other questions? Kindly raise your hand, please. Noor Khan has a question. Host, kindly unmute her, please.
Hello, ma'am. Can you hear me? Can you hear me, ma'am?
Loud and clear. Sauda, can you please see if there is any problem with his voice or mine?
No, ma'am. Your voice is distorting a little bit.
Okay, if it is okay now.
Yes.
Yes, ma'am. Can you hear me now?
Yes, I can hear you.
Ma'am, I get confused about this MPPT algorithm because the problem with the PV cells is only occurs when they are exposed to different shades. When they receive different
Okay.
sort of light, when different modules. So why?
Okay.
But at this time, what happens is that the panel which is in shade, it acts like a load, and if you are using MPPT algorithm, it's still.
Okay, so there are two different points. At first, it is recommended to. I hope your question is ended.
Yes, ma'am.
Okay, so can I thank you, Noor, for your question. I got excited with your question. It was very unexpected, but very good question. So you see here two different things. At first, we have to see the construction of a PV panel, which I explained you earlier. It is very important to connect a blocking diode with a PV panel. The MPPT algorithm is not supposed to direct a module to either behave as a generator or a load. An MPPT algorithm is only subjected to extract maximum power from the PV module under whatever condition it is operating and whatever type of curve it is generating. So this is a different talk. Now let's come to the PV system. So a PV system is basically responsible of generating a kind of curve which either module is responsible for directing the system module to either behave as a generator or a load. So whenever any of the module is subjected to shading condition, you are very right, it start to behave as a load. And there is a method, and this all phenomena is certainly known as hotspot condition. We call this as hotspot condition. And to avoid this hotspot condition, it is recommended by the PV manufacturer that each PV module should be connected with a bypass diode. And if you have, I hope you all have been through fundamental of electronics. This subject will be a part of your course. So if you remember the working of a diode as a freewheeling diode, as a blocking diode, and as a biasing diode, so you will be able to understand that this biasing diode with each module will help to prevent that module acting as a load. So this is not the responsibility of the maximum power point tracking algorithm. Maximum power point tracking algorithm has nothing to do with it. The algorithm is only responsible to match the IV operating point of the your PV system to the MPPT converter. That's it. This is what of an algorithm do. But why do a module behave as a load, and how can we prevent it? Obviously, if we are not connecting a blocking diode, the module will start to act as a load, and in that case, we will have a unique peak, but the overall efficiency of the algorithm will definitely be reduced. So if your question is that what is the use of MPPT algorithm when there is shading condition, so MPPT is only useful if you have used a blocking diode, a bypass diode with it, making sure that the overall efficiency of the converter is not being reduced. I hope my my answer is clear to you and was useful for you.
Thank you, ma'am. Does anyone have any more questions?
But I want his feedback. Did he understand the question, or I understand his question right? The answer was okay, Noor Khan?
Host, can you please unmute Mr. Noor?
It's equally important to see whether the audience is satisfied with the answer or not. Thank you, Noor. Thank you so much.
Yes, ma'am, I understand. But I have one more question, ma'am.
Yes, please.
As you said, it is effective when panels are in shaded, but still we can basically track the maximum power from in such kind of conditions. But don't you think, ma'am, overall efficiency of the system will be reduced? And one panel is actually
No. That is why we have maximum power point tracking algorithm. The whole objective of the algorithm is to track maximum power. So you see, when I tell you that the curve have multiple peaks, it doesn't mean that the maximum peak is not, at that time the PV system is generating that amount of power only. So from that system, the maximum power that can be extracted, the algorithm is supposed to extract that power without decreasing the efficiency of the overall system. So now this is the work of an algorithm. An efficient algorithm is supposed to extract the maximum power. So how can it decrease the efficiency of the system? Overall partial shading condition do decrease the overall efficiency of the system, but maximum power point algorithm are supposed to compensate it. Maybe I can say it in more simplified way.
Yes, ma'am. So why don't we actually move the panel in? We can use solar tracking systems to basically move modules to towards the solar radiations.
Are you serious? Let's come to
Yes.
some solar farming sites where a number of panels are installed. Do you think it is easy to relocate the panels? It's not like wind turbines that with wind they will keep on moving. These panels are solid objects, and it is really not easy to move and install a panel already due to the fact that they not only they are massive, they are heavy, but also because they involve a lot of electrical connections. Obviously, you are not going to use those panels are converted with some inverter, some grid connected system by means of wiring. It is never easy to install a whole to relocate a whole installed system from one location to another location every time the weather changes. Do you think so? And there are some unconstrained, unforeseen developments surrounding. Let's say a panel is constructed in a dense urban area. So the panel was constructed in an unshaded area, but certainly a building is constructed next to it. So now development area has been changed. You cannot ask them to not construct the building, or you cannot reinstall your panel from there to anywhere else. This is not easy. It's not practical, by the way. Okay, this could not happen.
Ma'am, thanks.
You just cannot relocate.
Thank you, ma'am.
Welcome. Any other questions?
Thank you.
Thank you very much, ma'am. Now we will proceed with our event. We would like to present a little something, a token of appreciation for our most esteemed speaker. On behalf of all the participants and our entire organizing body, we would like to thank you, Dr. Saba Javed, for humbly joining us today and giving us your precious time. It was an honor for us. Thank you so much.
Thank you so much, Sada. I am extremely happy to deliver this source of knowledge for you, and I'll be happy to join you all over again for any kind of seminar once again. Thank you so much for being so nice as a host.
It's my pleasure, ma'am. Thank you very much. We would also like to thank... Yes, ma'am?
Okay. Now you carry on, please.
We would also like to thank our participants for joining us today and showing interest in our events. As many of you may have noticed, we have been sharing a feedback form in the chat box. Kindly do fill it out since your feedback is very precious to us. And this will also secure your certificate. Thank you very much and goodbye for now. Allah Hafiz,
Thank
everybody.
you so much.